Now, in this lecture I will talk about mathematical induction. Mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, 5, 6, 7, etc. So when we prove something according to mathematical induction, we will make two stages. And in the first stage we will check if the statement is true for n that equals to 1, and only if we pass the test we will proceed to the next stage. We will proceed to the second stage. That is to say, we will assume that the statement is true for n, and we will prove it for n plus 1. And that is to say, we will create an expression for the statement for n, and we will assume that statement is true, and then we will prove it for n plus 1 as we rely on our statement for n, or as we rely on our assumption that the statement is true for n, and that assumption is the induction's hypothesis or induction's assumption, and we will prove that the statement is also true for n plus 1 when we rely on the induction's hypothesis that it is true for n. Okay, so now I will explain what is the logic behind mathematical induction. You should remember that in the first stage we check that the statement is true for n that equals to 1, and after we verified that it is true for n that equals to 1, we proceeded to the second stage. That is to say, we assumed that the statement is true for n, and we proved that it is true also for n plus 1. So we can say that we know that the statement is true for n that equals to 1, and according to our general proof that if it is true for n, it also must be true for n plus 1, we actually prove that it is also true for 1 plus 1, because n equals to 1 and n plus 1 is 1 plus 1. So we actually proved that it is true for n that equals to 2, according to our general proof that if it is true for n, it also must be true for n plus 1, and n equals to 1, so it is true for n that equals to 1, because we checked that it is true for n that equals to 1, and according to our general proof that if it is true for n, it also must be true for n plus 1, we actually prove that if it is true for n that equals to 1, it also must be true for 1 plus 1, that is n plus 1. That is to say, it is true for n that equals to 2. Okay, so in this way we proved that the statement is also true for n that equals to 2. And then we will repeat on the same process in order to prove that it is also true for n that equals to 3. Because we know that it is true for n that equals to 2, and according to our general proof that if it is true for n, it also must be true for n plus 1, we can say that it is true for n that equals to 2, and it also must be true for 2 plus 1, that is n plus 1. That is to say, it also must be true for n that equals to 3. And now that we know that it is true for n that equals to 3, we will repeat on the same process in order to prove that the statement is also true for n that equals to 4. Because now we know that it is true for n that equals to 3, and according to our general proof, we will prove that it is also true for n plus 1, that is to say for 3 plus 1, that is 4. Okay, and then we will repeat on the same process to prove that it is also true for 5, 6, 7, 8. So in this way we actually proved that it is true, the statement is true for all the natural numbers. Okay, so in order to clarify the topic, I will give you 2 examples. We will start with the first example. It is 1 plus 2 plus 3 plus n equals to n times n plus 1, all divided by 2. So we have to prove that this statement is true for all the natural numbers. So we will start with the first stage, that is to say, we will check that this statement is true for n that equals to 1. So in this side of the equation we will have only 1 because n equals to 1, and the other side of the equation we have n times n plus 1 divided by 2, and n is equal to 1, so it will be 1 times 1 plus 1 divided by 2 equals 1 plus 1 is 2, 1 times 2 divided by 2, 2 divided by 2 is 1. So 1 equals to 1. So we actually passed the test. We finished with the first stage because we proved that this statement is true for n. As you can see, because we add in this side of the equation 1 equals to n times n plus 1 divided by 2, so it is 1 times 1 plus 1 divided by 2 equals to 1 times 1 plus 1 is 2, 1 times 1 times 2 divided by 2, and 2 divided by 2 is 1, so 1 equals to 1. So now we will proceed to the second stage. That is to say, we will assume that the statement is true for n, and we will prove it for n plus 1. Okay. So we will assume that the statement is true for n, so we will create the first equation that it will be the expression for the statement for n. It will be 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So the first equation will be the induction hypothesis. So again I will repeat, the expression for n will be the induction's hypothesis. We assume that the expression for n, it is true according to our assumption, and then we will prove that it is true for n plus 1. So we will create the expression of the statement for n plus 1, and we will have to prove that the expression for n plus 1 of the statement is true, as we rely on our assumption that the expression for n is true. So the expression for n plus 1 will be 1 plus 2 plus 3 plus n plus n plus 1. We actually create the expression for n plus 1, so we will add numbers in this side of the equation until we will arrive to n plus 1, and all equals to, in the original equation we have n times n plus 1 divided by 2, but here we create the expression for n plus 1, so whenever it is written n in the original equation, we will write n plus 1, because this expression is for n plus 1. So in the original expression we have n, so we'll write n plus 1 times n plus 1, so n becomes n plus 1. We have in the original expression n plus 1, so it will be n plus 1 plus 1. Okay. So the expression for n plus 1 will be 1 plus 2 plus 3 plus n plus 1 equals 2. Instead of n, we will write n plus 1 times n plus 1. So in the original expression we have n plus 1, so the expression for n plus 1 will be n plus 1 plus 1, because we substitute n by n plus 1, because this expression is for n plus 1. So it equals to n plus 1 times n plus 1 plus 1 all divided by 2. So this second expression, we will prove that it is true according to our assumption that the expression for n is true. So we will rely on our assumption, or on the induction's hypothesis, in order to prove that the expression of the statement for n plus 1 is also true. Now here it is n plus 1, so it is n plus 2. So we will write it down. So the only expression from this line to this line is that we changed the expression n plus 1 to n plus 2. All the other things remains the same as this line. Okay, so the expression for n plus 1 that we have to prove that it is 2 is 1 plus 2 plus 3 plus n plus 1 equals to n plus 1 times n plus 2 divided by 2. So in order to prove the second equation of the statement for n plus 1, we should look on this expression. 1 plus 2 plus 3 plus n is actually this expression is actually exactly the same expression as this expression, and 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So we actually can substitute this expression 1 plus 2 plus 3 plus n by this expression n times n plus 1 divided by 2, because they equal to each other. They are equal to each other, so we can substitute this expression by n times n plus 1 divided by 2, so we'll do it now. So instead of 1 plus 2 plus 3 plus n, we will write n times n plus 1 divided by 2. As I already said, they equal to each other, so we can substitute each by other. And then the other expression, we will copy it as it is in the second equation. Here it is written plus n plus 1, so we'll copy it as it is, and it is equals to n plus 1 times n plus 2, n plus 1 times n plus 1 times n plus 2, all divided by 2. So we have to prove that the second equation is true. Okay? You can see that clearly that we have n plus 1 in both sides of the equation, so we can divide both sides of the equation by n plus 1. And we will get that n times n plus 1 divided by n plus 1 is n, and divided by 2, plus n plus 1 divided by n plus 1 is 1, equals to n plus 1 times n plus 2 divided by n plus 1 is n plus 2, and it is divided by 2. So we got that n divided by 2 plus 1 equals to n plus 2 divided by 2. So we can divide this expression to two parts, or we can separate this expression to two parts. Okay, so we'll do it now. So we have n divided by 2 plus 1 equals n plus 2 divided by 2 is, when we separate it to two parts, it will be n divided by 2 plus 2 divided by 2. Okay, so when we divide this expression to two parts, it will be n divided by 2 plus 2 divided by 2. Okay, now 2 divided by 2 is 1, so we'll write it down. So it is n divided by 2 plus 1 equals to n divided by 2 plus 1. So actually we got an identity n divided by 2 plus 1 equals to n divided by 2 plus 1. So actually we proved that the second expression for n plus 1 is true. So we can say that we generally proved that if this statement is true for n, it also must be true for n plus 1. That is exactly what we proved in the second stage. And actually, in this way we proved that this statement is true for all the natural numbers. Why? Because, as I already explained to you, we actually have already proved that this statement is true for n that equals to 1. It is the thing that we did in the first stage. We checked that it is true for n plus 1, and it is indeed true for n plus 1. And in the second stage we proved that if it is true for n, it also must be true for n plus 1. So now that we know that it is true for n that equals to 1, so it also must be true for 1 plus 1, that is n plus 1. N equals to 1, so n plus 1 is 1 plus 1. So it also true for n that equals to 1 plus 1, that is to say it also true for n that equals to 2. And then when we know that this statement is true for n that equals to 2, we will repeat on the same process in order to prove that this statement is also true for n that equals to 3, because we know that it is that it is true for n that equals to 2, and according to our general proof that if it is true for n, it also must be true for n plus 1, we can say that because of the fact that we know that it is true for n that equals to 2, so we also can deduce that it is also true for 2 plus 1, that is n plus 1, because n equals to 2. So, and in this way we actually proved that it is true for n that equals to 3, and then as we repeat on the same process, we will prove that it is also true for n that equals to 4, and then we will repeat on the same process in order to prove that it is true for n that equals to 5, etc. and etc. So in this way we actually proved that this statement is true for all the natural numbers. Okay, so I will give you another example in order to clarify the topic. The second example will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared all divided by 4. So we must prove that this statement 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared all divided by 4. So we'll start with the first stage, that is to say we will check if this statement statement is true for n that equals to 1. Okay, so in this side of the equation we will have only 1 to the power of 3 equals, in the other side of the equation is n squared times n plus 1 squared all divided by 4, and we know that n is equals to 1, so it will be n to the n squared times n plus 1 square is 1 plus 1 square all divided by 4, and this is equals to 1 square is 1 and 1 plus 1 is 2, so we have 2 square all divided by 4. So 1 times 2 to the power of 2 is 4 divided by 4, so it will be 1 times 4 is 4 divided by 4, and 4 divided by 4 is 1, so 1 equals to 1. So we actually passed the first stage, and we actually verified that this statement is true for n that equals to 1. Okay? now, only after we verified that this statement is true for n but equals to 1, we can proceed to the second stage. And in the second stage, we will assume that this statement is true for n, and we will prove that this statement is true also for n plus 1. Okay? So our inductions hypothesis will be that this expression is true for n. So the expression for n actually will be exactly the same expression. So the first equation will be the expression for n. And this expression we assume that it is true. And that is the induction's hypothesis. So the expression for n will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n square times n plus 1 square all divided by 4. So this is the induction's hypothesis or induction's assumption. We assume that this expression is true. Okay? The induction's hypothesis is the expression for n, and we assume that the expression for n is true. And as we rely on this assumption, we will prove that the statement for n plus 1 or the expression for n plus 1 for actually this statement is also true. So the expression for n plus 1 will be simply 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3. Why? Because the expression is n plus 1, so we will add numbers until n plus 1, so it will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3, and all equals to, in the original expression we add n squared times n plus 1 squared divided by 4, but here in the second equation is the expression for n plus 1, so wherever it is written n in the original expression, we will write n plus 1, because this expression is for n plus 1. So here it is n squared, the original expression, so we will write n plus 1 squared times n plus 1 squared. So instead of n, we will write n plus 1, so it will be n plus 1 plus 1, because this expression is for n plus 1. And all divided by 4. So in the original expression we had n squared, so we wrote in the second equation n plus 1 instead, n plus 1 squared instead of n squared, and then we multiply it by, in the original expression it is n plus 1 squared, so in the second expression it will be n plus 1 plus 1, because the expression is for n plus 1, so it will be n plus 1 plus 1 squared, and all divided by 4. And n plus 1 plus 1 is n plus 2. So we write it down. We copy the other expression as it is. So I already told you n plus 1 plus 1 is n plus 2. So we write it down. So it is n plus 2 square all divided by 4. So here the only change that we did from here is that n plus 1 plus 1 is n plus 2. All the other things is exactly the same. Okay. So here we will do exactly the same process as we did in the first example. We should look on this expression that is in the green color, n plus 1 plus 3 plus n to the power 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 is exactly the same as this expression. They are exactly identical to each other, but this expression equals to n squared times n plus 1 squared divided by 4. So we actually can substitute this expression by this expression because they are equal to each other. So we will do it now. So instead 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3, we will write n squared times n plus 1 squared divided by 4. It is equals to this expression, so we substituted it by this expression, and then we will copy the other things that left in the second equation. We'll copy it as it is, so it is n plus 1 to the power of 3 equals to n plus 1 squared times n plus 2 squared all divided by 4. Okay, I will repeat again. Actually we substituted this expression by n squared times n plus 1 squared all divided by 4. They equal to each other, so we can substitute each by the other expression, and then we copy the rest of the equation as it is. Okay, here it is n plus 1 to the power of 3 equals to n plus 1 squared times n plus 2 squared all divided by 4. We copy it from this line exactly as it is here. So actually, as you can see, the second equation that we must prove that it is true, we have n plus 1 squared in both sides of the equation, so we can divide the equation by n plus 1 squared. Or we can divide both sides of the equation by n plus 1 squared because we have n plus 1 squared in both sides of the equation. Okay. So n squared times n plus 1 squared divided by n plus 1 squared is n squared, and we divide it by 4 plus n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1 equals to n plus 1 squared times n plus 2 squared all divided by n plus 1 squared will be n plus 2 squared, and it is divided by 4. Okay, as you can see here, we divided this equation by n plus 1 squared, so n squared times n plus 1 squared divided by n plus 1 squared will be n squared, and we divide it by 4, and n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1, and n plus 1 squared times n plus 2 squared divided by n plus 1 squared will be n plus 2 squared, and we divide it by 4. So here we can multiply both sides of the equation by 4. Okay. And we'll get that n squared divided by 4 times 4 will be n squared plus n plus 1 multiplied by 4 will be 4n plus 1 equals to n plus 2 squared divided by 4. Okay, so after we multiply this expression by 4, n squared divided by 4 times 4 will be n squared, and n plus 1 multiplied by 4 will be n 4 times n plus 1, and n plus 2 squared n plus 2 squared divided by 4 times 4 will be n plus 2 squared. So we can open the brackets here. So here, after we open the brackets, we will have here n squared plus 4 times n is 4n, and 4 times 1 is 4. And here it is a plus b squared, it is a squared plus b squared plus 2ab, so it will be n squared for 4 plus 4n plus 4. Okay, so we have here an identity, and we actually proved that this statement is true for n plus 1, or in general we proved that if this statement is true for n, it also must be true for n plus 1. And in that way we actually proved that this statement is true for all the natural numbers. Why? Because in the first stage we proved that we checked that and we verified that this statement is true for n that equals to 1. And then in the second stage we proved that if this statement is true for n, it must also be true for n plus 1. And we actually can say that we know that this statement is true for n that equals to 1, and according to our general proof, it also must be true for 1 plus 1. That is 2. And from the fact that it is true for 2, we can also deduce that it is true for n that equals to 3, because we have our general proof that if it is true for n, it also must be true for n plus 1. And we know that it is true for n that equals to 2, so it must be also true for n plus 1, that is to say for 2 plus 1, that is 3, and we will repeat on the same process to prove that it is true for n that equals to 4 and 5 and 6 and 7, etc. So in this way we actually proved that this statement is true for all the natural numbers. Okay, so we can summarize the topic mathematical induction, and we can say that mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. And a natural number is a positive integer like 1, 2, 3, 4, etc. And we have two stages in the mathematical induction. In the first stage, we will verify that the statement is true for n that equals to 1, and only if we pass the test and it is actually true for n that equals to 1, we will proceed to the second stage, that is to say we will assume that the statement is true for n, and we will prove it for n plus 1. And in this way, as I already told you, we actually proved that the statement is true for all the natural numbers. Okay, thank you very much.